Fantastic. All right, so we've got a jam-packed schedule. So today I'm Scott. I'll be our tour guide. I've got with me Michael Shaler and Graham Gansel and a special guest appearance by Chris LaCava. Our next slide agenda, what we're going to cover today is really sort of what is it, sort of dive in a little bit of the art of the possible. Chris is going to give us a great demo. And then Graham is going to overview sort of how do we really get sort of get busy, if you will, with machine learning and the different elements. And then Michael Shaler is going to wrap it up with how does graph and specifically some of the tools that TigerGraph brings to the party. How can we do this at a different level? So that's what we've got on tap. So without any further ado, let's go ahead and jump in. Well, it's a wild world, right? Just this week, we learned that JBS Meat basically is paying their cyber ransom. But if you go through this, the takeaway is they started small. It started to sort of, chew at the edges. And now what we're seeing is it's much more sophisticated. It's no longer just ransomware. It's going in, if you're a bank and creating an account that looks real, it's transacting, perhaps even as a business, as a fraud ring, basically moves in a different direction. And the four or five sort of different cases that are out there that we've heard about are enormous, right? An $11 million payment because they can't get around it. That's a pretty big deal. So I don't think anybody out there today is saying cyber isn't important. But I think the key takeaway here on our next slide is we start to see it starts to cascade, right? So our use cases over on the left, where we have cyber, it's no longer just cyber in a silo. It's saying that cyber or ID falsification are typically linked. And then once I'm in the door, I may do any of these other use cases. So how do I empower the investigators in the center? How do I allow to do, basically do complex connections, connections of data, where is it going, et cetera, right? All the way over to the right now where I'm doing patterns. How do I recognize it? How do I act on it before it happens, right? That's really the crux of what we're going to see today. And it's no longer living in a silo, it's a connected world. On our next slide, what we start to see then is there's a couple of really key elements that TigerGraph and Expero can lean in on, right? So in these cases, our accuracy increases incredibly. So whether you're doing any of those use cases, these are just two samples of in the cyber, how do we increase the accuracy? We reduce the false positives as well and increase the productivity across these. And then even on the one on the right, which was a bank that was doing internal entitlements and how did people start to do things that were internal and external. The point of this is on our next slide, we start to see people are starting to use machine learning, and Graham's going to walk us through that. And that's really fantastic. You get a lift, and you should. And if you're not doing it today, you're probably behind the times. Where we're starting to see now this graph and machine learning starts to boost it. And then the final part of this is the visualization. And then even over the top is this learning loop that Graham will share with us, where now I can actually learn from the human, learn from the machine learning, and learn from graph to boost that even higher. And the point now is let's do some things automated and let's do some things where the human can teach the system. That's really what we're trying to show here. And we have empirical evidence. So that's exciting. On our next slide, why now, right? I mean, we've been doing this for quite a while. Well, COVID has really lifted sort of the water to see the barnacles on the boat. There's this whole idea of doing more with less. How do we cut those costs and drive that down? And whether you're in retail or banking or wherever that is, you've got to do more with less, and you got to do it in real time. This idea of bolting onto existing technology is extremely important. How do I do it today? How do I change the tires on the Indy race car while it's rolling is really our goal here. And so now what we see here is this stack of the different people, right? So now that I want to go do all that, what we are going to show you today is start at the top. Chris is going to show us a dashboard where we start to see the function, the feature, and then we go down into the heavy lifting at the analytics and even down at the IT at the bottom. Our goal here is that everyone has a way to touch the elephant and use the power of what Graham and Michael are going to show us, right, is how do we use that back end, things that seem hard, but now a regular human can harness the power of that. And that's what we'll see here in a minute when Chris gives his demo as well. On the next slide, let's talk about some of these things, right? So we're going to show you today a fabulous application. Michael's going to talk about the back end and the front end. And the goal here is that it's a 1-2 punch. We have the ability to do the heavy lifting on the back. We have the ability to do sort of that touching of the elephant for laypersons. And the goal now is to tie those together for your organization to get prescriptive and do it fast. So in our next screen, let's talk about sort of how that fits together. There's our friend TigerGraph on the back end, and here's now the toolkit on the next slide that sort of shows what that overlay does is it sort of comes in behind and wraps around it, right? That's really what we're trying to show now is that total picture of how do I get to solving cyber and get it done quickly. On the next slide, we start to see what do these things look like. So now touching that elephant, as we showed in the first diagram, could be showing people and then showing how that person's email got hacked and being able to break that down. Those may be two screens that two different individuals use or one person who integrates between the two. But let's make it easy. Let's take the complexity out of those kinds of things. So what we see in this, and again, Chris is going to show us more, is how do I jump into that and interact in a human workflow? On our next slide, something similar. Some people see things in grids. They don't necessarily have to see things, right? They see things in temporal, in time, or in sort of a geography. Make it familiar and make it easy, right? Give them a recommendation that they can act on. That's really what our goal is. On the next slide, we can see time. How did things happen? When did they happen? Who knew what when? That's part of the whole forensic activity that Chris will walk us through here in a minute. But it's very important to be able to look at the data in a graph in that other dimension. On the next slide, right? Now I want to see it in geography and I can see it overlaid with risk or color treatment, right? So how did these scores happen? Well, I ran a graph algorithm. Well, the lay investigator doesn't need to know how the algorithm was run that Graham will show us, but the fact that I need to act on it or I don't need to act on it may be just as important. In our next screen, right? Now we can bring it all together. How do I show it all in one place? How do I show different persons those different things? And then quite frankly, in this case, do I have a spider network of things that really turned into that? How do I shut it off in real time? How do I create triggers where different parts of the organization can react so that I don't end up paying that ransom? That's really what these sort of visualizations are. And then again, Graham and Michael are going to show us sort of how did we get to this prescriptively from the back end side of it. Okay, next slide. Now our special guest, Chris LaCava, is going to give us a demo. Chris, why don't you walk us through sort of a day in the life, if you will?
Sure. Thanks, Scott. Okay, so as Scott had mentioned, with our toolkit, TigerGraph SDK to build analytic solutions, sitting on top of a very powerful backend engine through TigerGraph, we're able to connect a series of data sets and get real-time insights into things that aren't necessarily easy to see unless that data is connected and you have that analytics power that is fueled by some of the connected data that is normally very siloed and hard to see the non-obvious connections unless you link them up in certain ways. So this is an example dashboard of activity within within a network. We're looking at various things that we could pull from logs very easily, but when we start to connect that data, we start to see a bigger picture. So we can see activity around authentication, maybe some emails that are flagged because of suspicious activity, or that suspicious activity could even just be volume within a certain period of time. We can track incidents, and then we've got other various network-based statistics that we can follow. This is always set over time, so that allows us to play this through and basically see how trends expand. And we've got macro trends here, where we can look at this even on a global scale. Where is various activities coming from globally, where the origins, as well as things that are very, very local to our network, such as things coming into the network, or even just activity across systems, such as failed logins. We can give a bird's eye view around news feeds and things of that sort, typical dashboard information. But this is where it gets interesting, where we look at these two boxes here. We've got a set of alerts that are looking at that connected data, and now starting to make assertions based on that, and automatically detect things that may not be very easy to see from pure human analysis, and is definitely time sensitive. So I think Graham will dig into this a little bit more, but we can actually train systems to look for certain patterns. And because that data is connected, those patterns basically have a fingerprint within the graph database. It's got a topology, a geometry, if you will, to it. And then we've got various things that we're watching here. So I'm going to dig into one of these really quickly here. Let's see here. So I've clicked into this alert, and it happens to be that that there's a host that is sending excessive amounts of email within a very short time frame. And I can see here that there's been a spike in alerts within the time frame that I'm looking at. And sure enough, there is a host. It looks a little bit suspicious here. And it is connected to someplace offshore. Imagine I'd be, sitting in the U.S. With, my systems are located in the U.S. here, and I see a lot of email activity with the same generic subject line here. It looks a little bit suspicious, going to a lot of different people in my organization. So this, this looks like typically the footprint of something like a fishing expedition. So I'm going to click into a little bit more information and just see what I know about that host. And sure enough, that host is pinged on a blacklist here that's been linked to malicious activity. So they've sent a lot of email into my organization. What I'm going to do is I'm going to basically select this subgraph here, and I'm going to create an alert to just build a detection sentinel, if you will, around activity that may, in its discrete form, not really get beyond the threshold of any single alert. But now that I'm looking at this in a holistic way, I can kind of start to allow the system to suss out those patterns. So I'm going to go ahead and create an alert trigger based on this selection. And I'm going to set a time date where it's effective and when I want it to run through. And then I'm going to set up a set of criteria. And the first one I'm going to say is, I just want to know anything that's within 10 degrees of connection to that malicious host. Now, anyone that received an email from that host in my system is going to be within 10 degrees. And then they're going to have additional connections to systems downstream from that, and up and other departments and things like that. But I'm going to cast a pretty wide net. But then I'm also going to say, I want to basically pull in a community that has anomalous activity that I may be looking at. One that may not be something that reaches a threshold, which would pop on my radar immediately, but in conjunction with its connection to this host, it starts to get interesting. And I really want to see a community. I want to see a cluster that I otherwise would not think to look at, because that's showing that potential malware based on that phishing exploit here may be spreading through my systems. And this email may be the backdoor in, but now they're starting to get to other systems. So I can set different weights based on those analytics and just attenuate some of the thresholds that I want that anomaly profile to trigger. And then I can say, okay, I want these actions to happen if something actually triggers. I'm going to want to schedule this not as a batch job in this case, but as streaming and immediate, because it's time sensitive. And I want it to report the results to a few different workflows, as well as put it on my dashboard. So then I just test the logic of that, make sure that trigger does in fact pass that test. and then lo and behold, as it runs, it triggers, and it's a very high risk. So now, with the lens of that, um, of that of that alert, I can go in and click and see exactly what it found. And sure enough, I have um, that host here, which sent an email to this account, which is held by this employee, and it has a bunch of different accounts, and it has a direct line to other anomalous activity. Again, it may not be that big of a deal from a trigger standpoint until I look at the holistic picture here. So now discrete things like, for example, a lot of files were renamed on this particular system, and there was a high volume of authentication. Now that may have been something that I would have not detected based on the threshold of my my alerts, but in conjunction with this, that community now pulls in. This is one employee in that community. We may want to look at that entire community and see how much this this stretches. But in this case, we have a direct line now to some suspicious activity. So I'm going to actually look in and see from a time perspective what this looks like. And if I look at just this employee's activity, I see some interesting things. I see a couple of login failed attempts that may or may not be anything. But then there is this period where we saw a lot of that file renaming and some other high frequency activity in these systems. But we can tell from the HR system and the time tracking system that employee in fact is on PTO. So this is a very suspicious case. We got this trigger immediately after we built that alert, so now we can run into mitigation and remediation quickly. Whereas if we hadn't set up that information, if that data hadn't been connected in the TigerGraph and allow us to run these analytics, we could have missed this for a month or maybe until something really serious happened. But we've got a shot now at shutting this down without much of anything in the way of adverse effects. So switch gears a little bit from this use case. This is another customer that we had done work on, or use case derived from that customer, where they were actually taking malware, running it in a sandbox, and then generating within a linked network the different behaviors that malware exhibited. Did it call out to a certain URL? Did it try to replicate itself? Did it access the registry? Did it do a very set of things? And based on that topology of what that looked like, they could get what initially looked like a nominal piece of malware, and actually using similarity matching, that topology or geometry matching in the graph, they could say, well, this actually shares attributes of these certain pieces of malware. So it's actually, another derivative of that, and that's something very common within the malware sets of patterns that we see, which is something may start out and then is riffed on and evolves over time. People take portions of that malware code and augment it to try to get beyond detection. So this is a use case that we worked on, where we actually were able to group these sorts of malware applications into a set of families, and basically lay out the family tree of these things, and that helped better detection, and also allowed people to proactively build responses to them. So a very distinct but in some ways similar set of activities to the use case I just talked to, and both are using this like highly connected data set of data shapes, if you will, to be able to do things like detection and similarity matching. So I will kick it back to the panel here, and Graham and Michael can actually tell you some of the details about how we've done that.
Thanks, Chris. I will take it over by starting off with a high-level view of where I'm taking you in my section. We have this screen here with various algorithms on it. Half are graph-based, half are machine learning-based. These all operate in conjunction in a real production system. We'll go through a few today. If you have questions about particular ones or how to implement these things, feel free to reach out or just ask questions in Q&A at the end of the presentation. So on the next slide, I'm going to show you a couple of algorithms that we found are particularly effective in the detection and prevention of cyber attacks. These few that I'm showing here are pure graph algorithms, and then later on in the last part of this section, I'll show you how to combine this stuff with machine learning to make a graph machine learning algorithm, which is what you would actually use in production. So when we look at the architecture of a system that deploys these things, we have sort of a logical flow that looks like this. Data comes in, data is normalized somehow, analytics are conducted, and then they are served to user interface or other microservices, something like that. So I'm going to do two different things here. First, I'm going to show you what data looks like in a cybersecurity setting in graph. And then the second half will be how do you do analytics on top of that and use graph and machine learning, as we just talked about. So stepping forward one slide here, we're just going to start with this first section and show you what this looks like in TigerGraph. So what's the benefit? Before I show you a data model, I just want to talk about, widely known story. I'm sure everybody on the phone here has heard of the SolarWinds attack that happened with a DLL injection attack. The point of this story in our context today is that attack was multi-vectored. So you can see the four sections here on the left-hand side, where there were multiple points of attack and multiple mechanisms of attack. And on the right, what we're showing is that using TigerGraph, you kind of have access to all of this data at your fingertips all in one place. And the reason that's important, of course, is because without that sort of contextual information from a variety of sources and full visibility into your operations, it's hard to detect attacks like this. And it's, I would claim, impossible to prevent them as well. Okay, so with that in mind, let's step forward and look at what a data model looks like. These are the various characteristics we'll talk about ingesting here into the TigerGraph database or cybersecurity platform. They are essentially everything you'd think about. I mean, it's really using a labeled property graph, storing that information in TigerGraph. It's really a beautiful system. I mean, it allows you to have information about wildly different pieces of contextual or behavioral information on one place. So like, for instance, you have your users stored in there. Their demographics are associated, but you also know the relationships between users, as I'm showing right there. And we'll show that momentarily. And then you have hardware characteristics. You have operations characteristics all sitting in this one location, so that when you perform the analytics we'll talk about later, you have the ability to sort of cut across not just a certain data type, but across an entire behavior, which is really important, as we all know here, in detecting cybersecurity breaches. Okay, so let's look at the data model here. This is a slide that I have swiped from the TigerGraph presentation, and I have a link to that later in these slides if you want to go deep on the data model. It is an awesome data model, and it has, just as we showed on the last slide, a bunch of rich contextual and behavioral information about how systems and users interact. So that's everything from like endpoints through servers, individual users, maybe there, and I'll show you in a second, the actual representations of user interactions physically with other entities, and then reaching out into the public web there. We can inject information, of course, of any kind of information we want into a labeled property graph. And one of the things we've found really interesting when you're doing analytics is actually shown on the next slide. So on top of this data model, you would inject information like we see here. And the reason that we want to do that is because as we detect attacks, as we're preventing attacks, we want to have a notion of sort of blast radius, effect, potential danger, or potential resulting loss from those attacks. And as we see here, this is an extract from what's called the 5.0 business ontology. There's a representation in this view of the actual like physical mechanisms that customers are interacting with in the real world. These, of course, are served by some digital hardware. And when you integrate the two data models, what you get is behaviors, not just actions, essentially inside of your cyber network. So that's a data model. Let me look now at what the analytics look like. So this is what we really want to see. This is what we're here to do, right? We want to detect and prevent fraud. And as I mentioned earlier, the output from this analytics, all of the analytics we'll talk about, is very simply fed into either a front end or any other consumer using the TigerGraph technology. And that's one of the reasons we like to use it so much. So let's look first at behavioral analysis. If we're looking at an injection attack from an endpoint that's sort of migrating through your system, that is a naturally graphy mechanism, right? So you want to trace, or what we might call traverse, I'll talk about that momentarily, the attack or the malicious code throughout the network. Wherever we find that it sort of subverts various security checks, if it can go around those in some way, those are all natural traversals inside of a graph structured data set. And behavioral analysis becomes, in that framework, it becomes a set of queries, right? So traditionally, what we've done in data science, in the world of cybersecurity, is we have come up with sophisticated clustering mechanisms to understand who our users are, who our endpoints are, who our servers are, with respect to their behavior on the network. And we can still do that. And we definitely advocate for continuing to do that. But we also advocate in this graph-based world for injecting that information, that analysis, that traditional analysis, into the graph framework, so that you can use these graph-based mechanisms like modularity or coloring, and then other types of topology metrics, like, I don't know, it could be anything like triangles or degree centrality, whatever, as a means to sort of up-level your clustering algorithms. And we'll talk about that at the end of the section too. All right, let's move on to sort of vector tracing. I mentioned this before. This is a natural query, a natural traversal in the graph space. On the left, we see a complicated graph there, colored by the neighborhoods that the nodes belong to. The nodes in this case are endpoints. And this is a little tiny subset of an enterprise's network, of course. And you can see, as a human being looking at that diagram, it is impossible to trace from one, let's say, malicious code injection, all the way through to which users, which endpoints it's affected. And we see that on the right-hand side. And what I've done here, because we can't show customer data, of course, is I've just taken a snippet from the TigerGraph documentation with their multi-hop pattern traversals. So in their new syntax, well, not so new anymore, but their version 2 syntax, it's actually quite simple, as you can see here, to define hops from a known injection through your network to a set of end users, which is exactly what we want to do when we're tracing, like, alerts, problems, could be known attacks back across our network. And with respect to that, on the next slide, I'm showing the actual calculation of what we would call blast radius, of course. Like, who is this affecting? What is the potential outlay? Those types of questions, answering those is, again, natural in this graph context. So this image you're seeing here is the same endpoint graph you saw before, but it has now been so-called page ranked. And if you don't know page rank, it's essentially like an algorithm that communicates the connectedness of those endpoints in the graph. And you can see those by size. And the idea is the nodes, the endpoints with larger circles on them here, with the bigger nodes, are more highly connected and and therefore are probably a higher net problem inside of your network. You want to attack those things first. You want to shut those things down. You want to make sure that those things are vetted and have been cleaned early on in your investigation. You get more power doing this in the graph, and this is likely, I have a few slides in this one because it's really important. Anomaly detection is very natural, again, in graph. And not only is it natural, like we saw with traversals, it's also, you get a different type of information, and that makes your analysis more accurate. So I have a couple bullets on the right there. The UI, by the way, is an example of some anomaly detection we did on top of graph database. On the right-hand side there, we inject that behavioral analysis from a few slides ago, and this is the new source of information you don't get without that graph-based structure. You actually have an algorithm, an anomaly algorithm running on the topology of the graph network. And that is something that you cannot do. You just plain cannot do it without graph-based structure. And then there's a couple bullets there about the types of attacks that's applicable for. Here's a cartoon version of that. So again, we're talking about behavioral analysis here. This is a representation cartoon of an unsupervised algorithm telling you which groups, which cohorts of, in this case, endpoints, but really could be anything. Could be users if you have demographic information. Could be servers. What they are doing in the network. And it's not like you know anything a priori about these groups. The algorithm traversing through the graph tells you, here are the groups. And then you have an analyst or investigator look through and say, this is a group of suspicious actors or suspicious endpoints, whatever the case may be, and dig deeper. So stepping forward, we have a less cartoony version. Here are some servers on the right with fake names on them, of course. And the colors there are the groups that they belong to, right? Those were detected by a combined graph machine learning unsupervised algorithm. And the colors are injected as indices into your graph structure so that when your analysts are looking at a UI, as we just saw 2 slides ago, they are immediately able to hone in on a particular group. And that is super powerful. I mean, the question very simply that I've posed here in one of these bullets is, hey, look at that yellow group. Is this behavior that we expect? Is this malicious behavior? Like, what's going on here? And then I have a picture on the next slide of a graph with a little bit more data, just to kind of show you what it looks like in a more realistic setting. The graph on the left, of course, is unstructured. It's before clustering, before neighborhood detection. The one on the right is the same nodes and edges. They've just gone through that clustering process and then been colored by their respective neighborhood indices. So pretty powerful, as you can kind of see here from that larger viewpoint. So let's go over to the next slide here, and look at the sort of culmination of all of this information. So we've talked about a bunch of algorithms here, but looking sort of at a more general level, let's say you want to have some sort of not just detection mechanism, but actual proactive like attack prevention mechanism. So maybe even before anything has gone wrong, can we detect vulnerabilities? And the answer is yes. So this is the link I mentioned earlier. Go check out TigerGraph's website for some excellent content. And again, just an extract from one of their presentations over there, which I thought was really succinct in regard to this topic, where they have this cartoon data laid out here, and they're showing you where the features are being extracted from that graph data structure. A couple notes there about the types of algorithms you might use to build up some graph-based features that you can extract for algorithms. Perfect. This is awesome. This is classic. And then on top of this, what you can also do is extract information not from like the nodes, which have red boxes on that slide, but also from the connectedness, the edges in between, we talked about a little bit earlier, and their structure, their geometry. That is a thing that is hugely powerful in all predictive analytics. And on the right-hand side, I've just collapsed some of those topology features into a 2-dimensional plane, so we can show how they sort of lay out in space. What's the point of all that? Well, once you have this information, you can inject it into a high-powered graph machine learning algorithm. And I'm showing that on the next slide. Well, we have a subgraph clustered large graph that we inject into, we put into a feature vector, those topology metrics. We then use a machine learning algorithm, a specialized graph machine learning algorithm in this case, to score things by their vulnerabilities and then populate that back into a UI. So that's a cartoon. This is on the next slide. We can see what it actually looks like. This is an output, a TensorFlow output of one of these algorithms. And you can see I've just put a little subgraph there on the left-hand side of the slide, but the middle there is the actual computation cluster for the TensorFlow algorithm that is doing that scoring. Before I wrap up, I've just got a couple of highlights here. So I wanted to show what the architecture of a system like this is. This is the TigerGraph platform. You can see in the middle of the slide there, various logic. We're noting machine learning, we're noting some graph algorithms, and we're also noting some business rules, some Boolean logic that you already have in-house, I'm sure, operating in your systems. That operates on top of a ton of different data sources. Essentially, any type of data source you want to integrate be piped in there. Here are some that we ingest and recommend for analytics. The output, of course, is a combined score from all of the vulnerability scoring mechanisms you have in place. And then feeding that information into the UI is not the end. What happens is you have explainable AI metrics in the UI, and those explanations are fed to the user, which then the user can say, hey, this was a good recommendation, or this was a poor recommendation. The actual system there, the scoring engine, will autonomously update itself by retraining those machine learning models. And that's what gives you that sort of fully recursive, adaptive system that is necessary, I think, for keeping up with cyber criminals in the space. So one more slide for you here. I just wanted to kind of showcase everything we talked about and wrap it up in its 4 categories. So there is a monitoring component, ingesting data, understanding whether that data is shifting over time. There is the deploying of the algorithms, right? Whether those be pure graph-based algorithms, pure machine learning algorithms, or that combo graph machine learning setting that we talked about today. There's active learning, which is the framework I just showed, which keeps that system fresh, keeps it updated over time. And then the interpretability metrics, which we didn't cover in this presentation, but if you're interested in explanatory reasoning over some of these complex systems, including machine learning, go click on the link over there when you get the slides and take a look. Thanks, everybody.
Graham, thank you so much. That was a fantastic exposition. I really value your insights into how machine learning and graph complement each other and really drive different outcomes. So now let's talk about the graph side of what Graham was talking about and focus on that. Before we get started, let's talk about TigerGraph, my employer. And the reason I came to TigerGraph is because when I was at DataStax, we brought in a graph component to the DataStax Enterprise stack, and we went far, but we couldn't get farther. And now with TigerGraph, we can scale out, and we can go much deeper, wider, and more profound insights into use cases like cybersecurity and ransomware and such. But really, we're the only scalable graph database for the enterprise, and we run on graph, we run on cloud, we deploy anywhere. We were founded in 2012. We were in stealth mode for 5 years. Our headquarters in Silicon Valley, but our crown jewels are really G-SQL, which is a SQL-like language that enables graph algorithms. PageRank, Louvain, others that Graham mentioned. It's really the best home for AI and ML. We answer the best questions about connected data with fast, deep, and wide insights. And we have some great customers who are really doing breakthrough work. Intuit's most interesting in this context because they actually use us for anti-fraud, cybersecurity, and anti-money laundering. And that's highly relevant to what we're talking about today. As you can see, Forrester thinks we're pretty cool too, just like Gartner does. So we're really excited about kind of where graph is going to help solve business problems that are existential and very, very important. Next slide, please. The call to action today is to see, connect, and act. We want to make sure we have the right architecture and pipeline. We want to ensure we connect to the right methodologies, and then act. We want to be flexible and plan for growth. Fighting digital criminals requires adaptation, and it requires new tools and new capabilities, and that's what we're here to help with. Click. So Gartner thinks that graph relates everything, and we want to ensure that we are helping our customers drive new insights from visibility, and that means that we also are going to blend data from multiple sources, and that means that we're going to have better machine learning and inquiries for more impactful business outcomes. Click. So let's talk about what a map to success looks like. What Graham just described sounds like very, very cool, but how do we make it happen? First, we have to see we have to build the enriched advanced persistent threat forensics graph. We need to connect that with external data sources, build an advanced persistent threat anomaly map, which likely includes external data sets and apps. We also need to understand the various employer, partner, contractor, and other machine access and interaction patterns. And then we connect deeper by doing human exploratory learning and unsupervised learning. And Graham's tool set is perfect for that. And then finally, we need to take action. We need to optimize operations and decisions. We need to ensure that we're extracting the right forensic graph features. And we have lots of ways to do that. But then we also want to train it and train the machine learning model with graph data, and then enrich the graph over time so that we can have a better chance of stopping crime in its tracks. Click. So how does ransomware work? Because this is kind of obviously the most the latest iteration, and again, it's an existential threat for some organizations. We're seeing hospitals and other organizations affected by this. And so the quick walkthrough is, and this is all goes back to what Graham was talking about in terms of focus on behavior. Part of this social engineering with a phishing attack, and then a message appears that you're trying to prevent the encryption mechanism to stop, and then that's when payment is demanded. And if you don't pay cryptocurrency, you don't get your files back. If you do pay, you don't know that you're ever going to be safe again, quite frankly. And so we've seen this happen time and again. And so the summary here is social engineering, machine-to-machine communications, and then cryptocurrency. Click. So this recapitulates that. But what's amazing to me, and quite frankly, it can be almost terrifying, is the fact that hospitals and the Colonial Pipeline and currency exchanges are all at risk. And it's a way to go from phishing to unencryptable files and operations to cryptocurrency. And what we need to do is find the crime rings, not just the bad actors. In other words, it's easy to find a bad guy. It's really hard to find the organizations that are behind the bad guys. And we want to help intercept and prevent them. And that's where graph and machine learning really make a big difference. Click. Why do traditional approaches not work? Well, antivirus hasn't solved a problem lately. Functional blindness is hard because of technologies like security information management systems. AI and ML it helps a lot. What Graham described is a tremendous step forward, but the best home for AI and machine learning is a connected data foundation. And then thinking like a hacker is kind of a cultural shift that means that we need to be smart and we need to move fast when we find out who's putting our assets at risk. Click. So how do graph analytics help? First of all, everything we're describing here, what Graham described is behavioral. That means it has a context in terms of source, destination, time, logical and material connections, account connections, and then cryptocurrency itself is the ultimate graph, or one of the ultimate graphs, I should say. It's all about connected behavior. how we can look into that and do forensics analysis on behavior in time is exactly what is needed. And that means that then we can leverage that connected behavior, that understanding of the connected behavior, turn into connected insights. And that means that, that once we can see into the bad guys, that keeps customers and customers of customers safe. So we are changing the game here because we're able to see beyond, anomalous behavior into anomalous connected behavior. Click. So how does this work? So we want to connect, we want to analyze, we want to learn, we want to see, connect, and act. And so we have a distributed graph database that enables us to build the advanced persistent threat anomaly map. We have net flow views, we have usage patterns, we have the forensic analytics that go into that. Click. We also then can add to that the advanced analytics and the collaborative investigation workflows. And then we can develop dashboards and reporting to report back to either stakeholders or regulators to click to do real analysis and real learning. That enables us to discover patterns, reduce risk, and optimize processing. So this is the full picture of what a graph can do, and machine learning, really makes the big difference here, as Graham said earlier, and Chris did it too. In terms of scalability, we need to be able to see deeply across many hops. We need to be able to see connections between accounts, beneficiary owners, ultimate beneficiary recipients. We need to understand the connections in terms of how that interacts with cryptocurrency. And then we also need to ensure that we're understanding at the core of this means that we're going to keep customers safe by knowing who our best customers are. And we want to make sure that the bad guys are kept out. And so we have to have a full, perimeter view of everything we're about. And that means that we can actually ensure that once we have connected all this data, then we can describe the golden path to a golden customer record. And then we can also ensure that we kept our perimeter and our interactions safe all along the way. Scalability is a must have. And we at TigerGraph are proud to say we can scale to petabytes. Click. But we also need to do real-time deep exploration. Actionable insights require seeing far and wide, and that means quickly. Is it a native graph? Is the way that the data is stored in the graph congruent to how the data is processed and queried, and how algorithms are run upon it, and then how machine learning is done upon that? Then the other part are you able to do full transactionality with real-time updates? Is it ACID compliant? Is it not just OLAP and analytics and algorithms, but also transactions, two-phase commit and all the rest? This requires updates to the graph, and we need to make sure the real-time updates are ACID compliant. And that's again the promise that we make. Click. So Graham talked about this in depth, and I think it's a really powerful set of statements that he made around what the connectedness between graph analytics and machine learning are. And the key question here is, does your graph database also support, let's go back, there you go. Does it also support a deep library of customizable graph algorithms? In other words, is it a black box, or is it something that you can tune for your particular use case? And for us, all of our graph algorithms are available on GitHub, and you see an example of PageRank here. And we can customize PageRank in a number of ways that are going to help drive better insights and better outcomes. Last piece is the language developer and algorithm and analytics friendly. Is it Turing complete? Does it have procedural and control flow elements? Turing complete means that you can express any algorithm in it, and G-SQL has that capability. It's our crown jewels, but it's also really changing how developers are thinking about graph analytics at scale. So we're really excited about how this has been embraced and how it helps solve for very, very difficult problems like cybersecurity and more specifically ransomware. Click. So let's talk about the design differences, why this is important, because this really does lead us to the conclusion that we think we can do more with graph database and graph analytics than any other approach we've seen so far, especially when we augment and empower that with machine learning. Starting up, with kind of the design differences that go into our features, we can do real-time deep link querying. We can do 5-10 hops. We can go all the way across a crime ring, and we can find out whose Bitcoin wallet where that landed for that particular ransomware attack. We want to intercept that and prevent that from happening. And that requires a view of a broad and deep and fast design that enables you to uncover hard to find patterns. And it needs to be operational, it needs to be real time, and it needs transactions and analytics. We can handle scale, we can handle petabytes of data. We have a distributed database architecture, which means we can scale across multiple machines in parallel in a very operationally simplistic way, simple way to manage and operate. Because we have massively parallel processing, we can take advantage of all of the CPU cores underneath us and do a lot of work very, very quickly. And I think the last point here is that we actually compress our storage to reduce the footprint, reduce data movement, and integrate all the data. So then in terms of what we do inside the graph database, we also could do analytics and machine learning in the graph. We don't have to export it off to an external system where we have a Turing complete language. We run in database, and then we can also run transactions in the database and accumulators for both OLTP and OLAP. That means we don't move data much, or we minimize the movement of data. We provide richer graph context, and then we can do machine learning on top of that. And the last one, which is the most recent set of features we've added in our new version, we actually support no-code migration from relational databases. And then we also have a visual query builder. That means we're going to democratize self-service graph analytics. And that means we can derive new insights from a broader range of users and investigators, and have an executive view into what needs to happen so that I can communicate to regulators, and I can also communicate to shareholders and stockholders that are going to want to know what I am doing about my cybersecurity posture and how I'm going to prevent ransomware from potentially destroying my business. Click. So TigerGraph Cloud is the best way to get started. tgcloud.io is a very helpful starting point. We have some starter kits there, and you can run our toolkit there as well. And let's talk about kind of a call to action, next steps. Click. Okay, so there's our website, here's our starter kits, and here's our fraud toolkit as well. And then Expero shows their website. They have some great demos. I really strongly recommend you take a look at their gallery. And then our fraud detection investigation toolkit is a great joint story as well to help deal with fraud, anti-money laundering, and cybersecurity. We are so excited to be able to share this information with you, and we'd love to answer any questions you have at this time.